Good afternoon, ladies and gentlemen. My name is Alexander Borgraaf, and I work at the research unit Lasers and Optronics, which is part of the CISS department. And I will be speaking to you about free space optical communications and its possible military applications. So when we are talking about free space optical communication, we first need to put that into its context. And that context obviously is the use of radio frequency communication. So radio appeared on the battlefield in World War I, and it hasn't left since. So commands and intelligence information were transmitted first via Morse code, then via voice, and these days in the form of digital data. Telemetry of rockets, satellites, and space exploration probes pass over radio frequency, as well as missiles and remotely piloted vehicles. Even navigation, such as GNSS, uses the RF band. But as useful as radio has been, it does come with some issues. And in a military context, the main problem with radio is the fact that if you transmit radio, your opponent can detect that you are transmitting radio, from where you are transmitting radio, and possibly also which messages you are encoding in your radio transmissions. And this information comes with some serious consequences for the operational units involved. Another problem manifests itself more in peacetime because the RF spectrum is not free. It is managed by local governments, which need to be asked for permission to use that particular part of the spectrum, and they need to grant this permission before you can use it. And even in wartime, a large part of the spectrum will still be reserved for civilian economic activity, because even in wartime, life goes on. And from this arises the third issue. Even if one would try to use the RF spectrum without permission, the spectrum is quite congested, and it has a finite amount of space. It is not possible to cram everything into the same bands. And with the implementation of 5G, this problem will get even bigger in the near future. So a possible solution for these problems with radio is to move outside of the RF spectrum into the visible and infrared domain. So the amount of available spectrum is vastly larger than the RF one. Light-based communications are almost by nature directional, which means that there's no overlap between nearby transmissions, so you do not have the congestion problem. And there is an extremely low probability of detection and interception because of this. The spectrum is unlicensed, so this solves a lot of the problems with radio. And this technology is what we call free space optical communications, also referred to as FSO or FSOC or FSOC. So what is free space optical communication? Well, you have a light source, receiver, and transmitter, typically lasers aligned at a distance. The beam is modulated to encode the information you wish to transmit, and this way you end up with a kind of high-speed wireless fiber. Typically we use lasers, but the example in the picture from 2001 used LEDs, so it is not limited to laser technology. So what are the components of an FSO system? Well, first there is an optical modem, which typically is very similar to even identical fiber optics communications modems, which encode the data on an optical laser signal. Then the second component is an FSO terminal, which is typically mounted on a pan-tilt system, which provides the PAT functionality, positioning, acquisition, and tracking. And then also contains the transmission and receiver circuitry. So the lasers emitting the beam and the photodiodes reading out the beam, and then the optics guiding one onto the other. And all of this is controlled by a computer system. So how does such a system operate? Well, it consists of two FSO terminals mounted on pan-tilt systems, which are trying to find each other, and then when they find each other, they point at each other as accurately as possible. They find each other through either known coordinates, RF transmitted coordinates, or possibly a visual or near-infrared beacon, which is then detected by an acquisition camera, a computer vision system, and then used to align the two telescopes. After that alignment, there's typically a need for some fine-tuning alignment to optimize the received beam, and even to couple the beam into a fiber communication system so it can be read out directly. So in this slide, you see a diagram of an FSO terminal. So in this case, the optics use a Cassegrain telescope, so you have the parabolic mirror concentrating the incoming beam, which is then sent through the hole in the mirror on a fine-tuning mirror, which then passes through the beam through a beam splitter on a quadrant detector, which optimizes the beam by having all quadrants being equal. And then, in this case, the beam ends into a fiber coupling setup, which then gets sent to the decoder and to the computer, so the data is received. To align the two telescopes, there is an alignment camera mounted, which either detects the beam itself and tries to center it into the frame, or detects an additional beacon, which is sometimes mounted around the telescope's opening. And then on top you see the transmitter infrastructure, which is basically the laser sending the modulated data to a mirror on the outside of the telescope, which then gets bounced off on a second angled mirror in the center of the telescope, so the beams are coaxial. And in the picture in this slide, on the right, you see an example of a commercial FSOC terminal by the company Mynaric. But you can see that there is a telescope mounted on a pan-tilt system. We are, of course, interested in the military use cases of this free space optical technology. And for this, we have participated in the NATO group IST-199 and its predecessor IST-ET-115, which had as objectives to develop recommendations for standards for FSOC use in NATO. Now, the first thing to look at is, of course, does this exist in the civilian world already? And civilian use cases do exist in space. So it is being used in intra-satellite communication networks. For example, Starlink uses them or has started to use them, and ESA has developed some. So this is definitely a thing, mainly because the positions of the satellites are predictable, and there is no atmospheric interference cause problems. Ground station to space has also been demonstrated, where there is an atmosphere in between, but of course the top layers do not affect the laser beam all that much. But so the NATO group identified 4 main military use cases, which were called on-the-move terrestrial operational use, portable land and sea use, manned to unmanned subsurface use, and then long-range terrestrial use. The first use case implies a battalion up to brigade size unit on the move, which requires a secure communication with low probability of detection and low probability of interception between moving vehicles. So the requirements for this were determined to be that the range of the system should be 1 kilometer for ground vehicles, 2 kilometer if you include airborne platforms, with a tiered approach. So maybe battalion doesn't have the airborne components, the plane, and the brigade does. Data rate should be around 1 gigabit per second. The accommodated ground speed should be 80 kilometers per hour. It implies a vehicle mount with position acquisition and tracking system with 360 coverage, 90 upwards for the air link, and the aerial platform covers the situations where line of sight is blocked, and it might also link to SATCOM for strategic reach back. So if you look at what technology is already available, then we see that commercial off-the-shelf systems are mostly developed for static applications, and some are used for aerial systems, and those are the ones which are the most promising. There's really some developments necessary in the VAT part of the system and beamforming to deal with atmospheric conditions. And currently, these systems have RF acquisition to determine where the system is, and it would be nice if this could be replaced with optical systems, so it could be totally radio silent. In the second use case, portable land and sea, portable implies transportable via vehicle, trailer, or ship, and possibly deployed quickly on masts. So the requirements for this system would be range 1 to 30 kilometer line of sight, with the actual range depending on the weather conditions. Data ranges should be between 1 and 20 gigabits per second. And if we look at size, weight, and power constraints, we're talking something of 50 by 30 by 30 centimeters, below 20 kilo, and below 600 watts in power. If we look at what is available in this technology, then we see that commercial of this shelf does not fulfill the range requirements. These systems are also not ruggedized, definitely not for sea. There's often no standardization, so having different systems talk to each other is a problem. In the maritime environment, there's some work which needs to be done for the BAT because of stabilizations on a moving ship, and the required long range is affected by the atmosphere. And what is needed to improve that would be things like atmospheric modeling, adaptive optics, which are also used in astronomy. So the third use case is a bit of a different one, in which we are looking at the communication between manned and unmanned subsurface vehicles. So navies use remotely piloted vehicles more and more, also in the Ukrainian war, for example, USVs on surface, ROVs, AUVs below the surface. To control these systems, we need a reliable link, and wireless links underwater remain a problem because radio doesn't penetrate that well, and optical systems also don't do terribly well. But there is some work which is partially being pushed by the oil and gas industry for pipeline monitoring systems. So if you look at the requirements for this, the range should be between 100 meters and 1 kilometers. Data rates can be relatively low, 100 megabits per second. The speed of the moving vehicle is below 5 meters per second, and you will have to have bidirectional position acquisition and tracking. If we look at what is available, yeah, there is no commercial off-the-shelf system which requires the data rate nor the range. But there is some technology in development by, amongst others, SA Photonics and MIT Lincoln Labs, which demonstrated an ROV using blue-green lasers and reaching a range of almost 100 meters. So the final use case, long-range terrestrial, involves strategically placed long-range FSO systems to replace satellite communications in a satellite-denied environment, and which would also be used to extend strategic communications into areas of operations with degraded infrastructure, either through bombardments or sabotage. This kind of system should be interoperable with the FSO systems of tactical units, which can then plug into this long-range network as a backbone. The requirements for this one would be a range between 35 and 50 kilometer, data rates between 1 and 20 gigabits per second, and swap not that very different from the other cases, like 50 by 30 by 30 and 20 kilos. And the goal is to set up a mesh network of tower relays, so static systems similar to microwave relays, which can then interoperate with other units. If you look at what is technologically available, this is the easier one of the use cases, because swap concerns are not that applicable on if you put everything on static towers. Also, the PAT is easier, and so this technology more or less exists commercial off the shelf, and it can also be integrated with high altitude pseudo satellite platforms to extend the range even further and to really mimic satellite communication. So as far as the standardization effort is concerned, the main problem is interoperability. This is a thing which requires standardization of the encoding algorithms, of the used waveforms and frequencies, of the types of optics, of the alignment strategies. The capabilities of the PAT systems are very much determining the performance of FSO systems. But if you impose a standardization, this might restrict innovation, because this is really the field where innovation is necessary. So a proposed NATO standard should restrict itself to standardizing the performance of a system, the required performance, and not necessarily the type of components. For standardization, there are some examples to build upon. So for space-based optical communication, there is the CCSDS, which has several publications on best practice for this technology. Within the fiber optic domain, yes, there's the ITUT, which has recommendations for the fiber equipment standards, and IEEE has standards for the encoding, so the physical and MAC layers. And if you look at the optical wireless communication, such as Li-Fi, there's also a standard by ITUT, the G9991 standards for short-range OWC, and IEEE is developing standards in this field. So, to come to the conclusion of this talk, we've established that while radio frequency communications are incredibly useful, they do have drawbacks. Free space optical communication solves a lot of these problems. One, due to not congesting the spectrum, and two, by having extremely low probability of detection or probability of interception. In the search for a NATO standard, we have identified 4 main use cases varying in scale and including one very specific submarine application. If we look at the existing commercial off-the-shelf technologies, we see that they work, and they work really well, but they are not yet suited for the specific military application in these identified use cases. And if we can implement a standardization, this could guide the development of the technologies in the industry in the right direction to solve these issues. And one thing we also notice is that positioning, acquisition, and tracking on the one hand, and interoperability are the two key elements needed to make this technology viable. If you have any questions, I will be glad to